Hmm. And this is what we have learned last time. And we mentioned that we want to solve an equation so looks like this: fx equals to 0. And we talk about the bisectrous method, and then the bisectrous method is looks like this. We just divide the integral into two parts and then getting the nodal point. Just get the nodal points of the original integral, and then we text the values at this middle point. And then there are three cases. The case one, the middle points the function evaluated at the middle point and then equals to 0. And then we can say we can conclude that okay, that for the P1, and then this is just the solutions to that fx equals 0 equation. And there are two other cases. And for the other two cases, we have either the f values evaluated at the P1, and then it has the same sign, it has this opposite signs as the f value evaluated at the left endpoint. Then we would choose this A, and then the P1 to be the new interval. And if that is another case, and the f value evaluated at the middle point and has the opposite size with the f value evaluated at the right endpoint B, and then that is the time we should choose the interval, the new interval as the P1 and B. And this is how the middle point things works. And then let me see. I actually show you one example how to choose that the new interval here. And due to some, let me see, does it work today? Huh. Copy image content. Okay. So what I'm going to do, copy image content. Oh, copy. Okay. Wait for a minute. At least it's working. Okay. That's not too good. Let me see. Okay. Let's just continue our discussions here. And last time I mentioned that we have the bisectrous methods, and the bisectrous method, it should look like this. I'm going to show you something because last time the copy and paste does not work. But today we have the luck to take a look at their methods here. So I also mentioned that the things we need is just 2 storage places and then 3 storage places, and that is for the left endpoint and right endpoint and the middle points. In the other things, we just need the hey, come on. Okay. Let's just skip this part. I hate this. Okay, sorry. And I hate this one. Just skip this part, the copy and paste things, the image things. So let me just write that down one. So last time I just mentioned that for the algorithms, you can go out to take a look at the algorithm you have on the textbooks. You just have the A and then to storage the left endpoint, and you just need to B to storage your right endpoint, and your the P to storage your middle point. And the other things is to compute the evaluate the functions at these points, and then choose the opposite size value, and then to be your new A and new B, and middle point. And here, and I also mentioned that you can have several stopping criterion here, and you can compare the different middle points from the different middle points from the different situation, and that is the current middle points, and then to the previous middle point, and then if it is small enough, the difference, and then we can stop it here, and then or the relative difference is smaller than the epsilon. And in other things, it could be the functions value at the P and the middle point, and then it could be smaller than epsilon. And this indicates how far we should go to the right hand side equals 0 here. And this is the stopping criterion. And we also mentioned one things about the very important things here. And then it's just the convergence rates of the, oh, that works. Oh, that's good. So here, you will see this happens. And this is the algorithm I just mentioned. And we have the P here, and then you will see we just need one variable here in the computer, the P and A and B, and that's it. And then you have your stopping criterion here, somewhere here. And this one FAFP, and then this one is just to compare the sum of the value at the left end point and the middle point. And also this one, if you take a look at this one, the stopping criterion here, and then this is if the middle point, the f function evaluate at the middle point A equals 0, and then we can stop here because the P is automatically the solution of the function. And this one means this is the same as the if you translate this a little bit, and then it's just the length of the interval is small enough, and then we can output our middle points, and then the P here to be our approximations result. And this is the algorithms we want, and but you can definitely change the stopping criterion here. And the next, we are going to take a look. We have already taken a look one example, and then we also claim that there's a convergence rate here. It's related to the iterations number we have, and then because it's bisections, and then bisections, which means that because the bisection it is related to the number of 2, and so here the convergence rate is O, big O, and then 1/2 to the end. So today we are going to show this proof here, and I'm going to write the theorem down first. So first of all, don't forget that every time before you go into the iteration, you need your input. Your input is, and do I write this one down here? So here, before you get the input into A and B, and you need to double check that your FA value and the FB value has the opposite side. And this is the direct input. And if they have the same sign, then you need to reconsider your input for the algorithm. So let's take a look at the convergence theorem here. The convergence theorem here, this is the theorem 2.1 on the textbook. Yes, you're right. We are going back to the previous chapters on this textbook, but it's the chapter 9 on the UCSB professor's textbook. But this textbook saying this chapter is easier than the others, so it put it to the chapter 2. So here we have, first of all, you have the continuous function on the interval A and B, and you require the function, the values is smaller than, product is smaller than 0, which means that they have the opposite side. And now the bisections method saying that, the bisections method is saying that okay, it would generate, the bisections method generates a sequence of middle point, and then this middle points, we are using the Pn to denote it, n equals 0, n equals 1 to infinity, and it's approximating the 0 of, or a root p of the f function. And so the root means it means this is the solution of fx equals 0. And so now we are going to claim the convergence rate, and then the convergence rate is the p is the root, and then the approximation is the pn, and then so the area, the difference between them, and then take the absolute value, and then it's smaller than or equals to the original interval length, and then divided by 2n. And when the n is bigger than or equals to 1. So now we are going to solve this one. First of all, we are going to take a look at this. So for any n is bigger than or equals to 1, and then we have, because this is the right endpoint, and then this is the left endpoint of the subinterval, and if we take a look at length of this one, and then it's just equals to the b minus a, and then 2n minus 1. And this is because, so for the first situations, let's take a look at this picture. So for the A1 and B1, and then you have the original length, and we have the, so for n equals 1, and then we have the b minus a. And then for n equals to 2, and then you would say the A2 and B2, the length of this interval is just half of the original one. And so we divide it by 2. And if you take a look at the A3 and B3, and A3 here, and then B3 here, and then B3 is the middle point of the A2 and B2. And so if you take a look at the length of the A3 and B3, and then it is just half of this length of the interval. So once again, we have for the b n equals 3, we have b minus a, and then 2 squared. So we can conclude that for this proof here, for n equals to, for the n, for each n is bigger than or equals to 1, and then we have the bn minus an, it's just a b minus a, and then divided by the 2, and then n minus 1. This one n equals 3, and then this is the 3 minus 1. So this is the first things we have. And we know that for the bisections methods is in this interval, the solution is in the interval an and bn, and which means that if we, so there's another thing, the middle point pn is just the an plus bn, and then divided by 2 is inside this interval, and for all the n is bigger than or equal to 1, and it follows that we have the p, and then minus the pn, and is smaller than or equals to the 1/2, and then bn minus an, and then b minus a, and then 2n. And this is because, so let me draw the picture here. This is the an and then bn, right? Let me see. Yes, this is the interval an and bn, and then your middle point is here, the pn. And the solutions is either on this subinterval, or the solutions is in this interval. So the difference between the p and then the pn should be less than the should be less than or equals to the 1/2 or this interval. Does it make sense? So here, this is the Pn, and then the P could be here, and then the P could be here. And then the difference between the P and the Pn should be less than the length of the interval here, or it should be less than the length of the interval here. And then the length of the subinterval here should be the 1/2 or the Bn minus An. Does that make sense? So this is the proof, and then it's quite easy. So I might put this to the final exam as well, because it's easier. So now there's one more type of the questions here. You have already know the convergence rate, and then we are going to take a look if the function is given, and then if the interval is given, and then how many iterations do we need to get the solution, the approximations with the tolerance. So there is one example here, and then it's examples regarding this convergence rate theorem. This is example 2 on the textbook. We have, so we need to determine the iterations number. Iterations number necessary to solve the so let's see, the functions, it looks like this. To solve the fx equals to x cubic, and then plus 4x squared, and then minus 10, and then equals to 0. And this is our function fx, and then equals to 0. And the tolerance, this one with accuracy, and then this is the tolerance accuracy, and then it's 10 negative 3, and then we have the interval using the initials interval A1 1 and 2. So first of all, you might need to double check that the FA and then F1 and then times the FB is smaller than 0, so that we can use the bisections method here. You can double check this one. But here, let's calculate the iterations number needed to solve the equations within that tolerance number. And this is the solution here. And so let's see so here from the theorems 2.1, and then we actually have P minus the Pn, and then it's smaller than or equals to the B minus A, and then 1 2 over n. And what is the B minus A here? And then the B is just 2, and the A is just 1. So we have this. So B minus A, and then this one is just 1, and then over 2n. So on the left-hand side, this is the error of the approximation, and then on the right-hand side is the BAM. So we want this BAM to be smaller than the tolerance number, and then that is 10 negative 3. And we can solve this equation. You can use your calculator to solve it. But I'm going to give out one idea here. And I'm going to take, you can either take the logarithm regarding to 2 and with the base 2, and then, or you can take the logarithms with the base 10. I'm going to choose it to be the logarithm base 10 here. So let's take a logarithm with base 10 on both sides. This is because I'm choosing the base towards to the tolerance number. I got this one, And first of all, I'm going to revise this one a little bit. And then this one is just a 2 to the negative n. And if I take the logarithm and then I got logarithms and then 10 and then 2 to the negative n. And then it's smaller than logarithms 10 and then 10 negative 3. And which means that I got this one. I got the on the left hand side, I got negative and then n and then logarithm 10 2. And then on the right hand side is just the negative 3. And which means that the n is bigger than the 3 over logarithms 10 over with the base 10 and then the number is 2. And if you use the calculator to calculate this number, it's around 9.96, and then we need to rounding up a little bit. So at the end, the least iteration number we need is 10. It should be the small n here. The least iterations number we need is 10. And I'm going to show you one more thing. And in case that you forget the logarithm, how the logarithm function looks like. And so this is the logarithm function. And this is why we have when we taking the logarithms functions on the both sides, and then we don't need to change the sign. And this is the logarithm function. And if you look at the logarithm function, and then you would say this is an increasing function, and which means that if this one number is the number here, the 2 to the negative n is smaller than the 10 to the negative 3, right? This is the inequality from there. And then when we take the logarithm function, and then it would keep taking the order of the relationship here. And because the 2 to the negative n is smaller than the 10 to the negative 3, and then when we take the logarithm, and they will stay the same order. And then the logarithm of this value and is smaller than this value. This is because this function is increasing function. Does it make sense? It does not change the sign, because if you have a smaller value here, let's say the 1 is smaller than 2, and then the x-axis, the 1 is smaller than 2, and then when we take the logarithm, and then the value of at the 1, and then the value of the 2, and then this one, the number on the blue line is smaller than the numbers on the blue line as well. This is because this function is an increasing function. So we will keep the same order here, and then we have the left. This number is smaller than this number, and then when we take a logarithm, and this number is smaller than this number. And so if you go back to take a look at the logarithm calculation, and then we can put the n, negative n to the from, and then the base here is 10, and then with the 2 number here, and then this is the negative 3, and we change the sign a little bit because we need to divide both sides by the negative logarithm things. If you divide the things by the negative something, and then we need to change the sign here. This is why we have from the smaller than side and then to the greater than side here. Does that make sense? In case that you cannot understand why we change the sign here to the smaller sign to the bigger than, greater than sign here. I just explain it because it's increasing function, and then we don't change the sign at the first, but we divide both sides by the negative logarithm with the base 10 and then 2 here. And this is why we change the sign at the end. This is how you calculate how many steps you need, iterations you need to get the desired result. And this is all the things. Any questions by so far? This is all the things about the bisections methods. Bystander methods is good, but people find out that there's a better method. It's called fixed point iterations method, fixed point methods. And this is the next part for the fixed point methods. And then we need to first, and then to get an introductions on fixed point problem. Fixed point of a function, and then it means that. So let's see. This is the definitions of the fixed point problem. Definition of fixed point. So if you are given functions, and then there's a point, and then the number p, we call it as a fixed point for a given function, and then this is a given function gx, and if the point here, if we evaluate at the evaluate this functions at p, and then its number is equals to p, and then we call it as fixed point. You can definitely see this why we call this a fixed point, because we evaluate the function at this point, and then it doesn't change the value, and then it just stays there. And this is the definition of fixed point. And don't forget the original purpose, the whole purpose of this chapter. The whole purpose of this chapter is to solve. So the whole purpose of this chapter is to solve this equation, fx equals to 0. So now we introduce another concept here, is fixed point. And we are going to get the connections between these two problems here. We are going to give you the connections between solving this equation and then solving the fixed point problem. And so for the connections here, I'm bringing the connections between this problem, these two problems. So for examples, if you are giving a problem, if this is a root finding problem, and then at p equals to 0, we can actually define a function gx based on the given problem here, based on the fx, and so that the problems at p equals to 0, and then it's equivalent to the gp equals to p, the fixed point problem. So for example, there's one example here. For example, we can define the gx in this way. The gx equals to x minus fx. Then we have the fixed point problem, and then we have the fixed point problem. The fixed point problem is solving the x minus fx, and then equals to x. And this is the fixed point problem, gx equals to x, right? So as you can see, I just changed define the gx in this way. And the fixed point problem, we can change it with this function, and then the fixed point problem for this function is gx equals to x. And if you take a look at the expressions here, it's equivalent to fx equals to 0, right? So this is one way to change the root finding problem. This is the root finding problem. We want to find fx equals to 0. Now it's going to change to the gx equals to x. And this is one thing we can do. And you can define the g functions in many ways. And then we are going to give you some examples later on how to there are many ways to define the gx function, and then we need to find out the proper g function to get the desired result. This is one way if we have the root finding problem, and then we get to the fixed point problem. And there's another way, and the connections between this root finding problem and the fixed point problem. If we have a fixed point problem, so for examples, we have a fixed point problem here. And it's the gx equals to x. Then now we can definitely define the function f(x) equals to the gx minus x. Then it is changed to, and then the fixed point problem. The fixed point problem can be changed to, can be converted to the root finding problem. And this one, it is just the f(x) equals to 0. The f(x) equals 0, if you take a look at this one, and then it's just the gx minus x and then equals 0, and then it would become back to the fixed point problem here. So they are equivalent. This makes sense. So you can switch between the root finding problem and the fixed point problem. And this is the things. And the next, I'm going to give out one example to find any fixed point. So to understand these concepts, because the fixed point is pretty new to you, although you have used one of the proof process in the take-home exams finals in the last quarter, it's quite similar. I will mention this later. And you have used these concepts in the last quarter, but you don't know the definition of fixed point. So, but now let's try to understand this fixed point concepts a little bit more, and then by one example. And so for this example here, let's find out determine any fixed points of the function. I'm going to use some shortcut here. FCM means map function. And then gx equals to x squared and then minus 2. So if the examples is asking you to find a fixed point, and then what does it mean? It means that we want to have the g value evaluated at x, and then it equals to x itself, right? So this means that we are going to solve this. We are going to solve the gx and then equals to x. And this is by the definitions of the, fixed point. Does it make sense? Because we evaluate at x and then it equals to x. It doesn't change the point positions. And so we are going to solve this equation, which means that we need to solve x squared minus 2 and then equals to x. This gives us x squared minus x and then minus 2 and then equals to 0. And we are going to factorize this a little bit, and then we have x plus 1 and then x minus 2 and then equals to 0. And this gives us two fixed point here, and then we got x equals to -1, and then we also have another fixed point, x equals to 2. And if we take a look at the pictures we have here, and you would definitely figure out that the meaning of the topology meaning of this solution. And it's here. So we just solve this equation, and then it's the same as if you take a look at the function here, we are solving gx equals to x. So which means that if you take a look at this picture, it is the same as finding the intersection points of this curve and the line here. And then the line is just y equals to x. And then the curve, the parabola here is x squared minus 2. And we are, by solving this equation, gx equals to x, and then it is equivalently to say we are finding the intersection point between these two between this curve and this line. And this is the first intersection point is -1, and then this is the second fixed point and the intersection point. Sorry, and this is the second intersection point is 2, and this is the same to what we have in the solution here. This is how to understand the fixed point. Any question? So it is just the intersection point of two, one curve and one line here. And so this is the introductions to the notation here. And now I'm going to give you the proof of, give you the statement of the fixed point methods. And the fixed point methods, the theorem here, the proof of this theorem is pretty the same as the last quarter take-home final exam. And then this is the theorem 2.3, and it's all about the fixed point method here. So there is two things here. It's about the uniqueness and the existence of the fixed point. And it's all about the uniqueness. So first, it's about the existence and the uniqueness of the fixed point. And I'm going to give out the statement here. So the first of all is about the existence. And for this one, we need to pose some assumptions on the g function, and then we get the existence. So first, we need the g to be the continuous function, and there's one very special requirement here, and the range. This is the range. The range, the gx. Let me just write it in this way, and then later on I'm going to change. So this one, it means that the range of the gx is also a subset of A and B, and you can translate this part as this way. And this is the assumptions. This is the gx is in the A and B, and then for all the x in the A and B. This is the domain. This is the domain, and then this is the range. And the range, it should be inside the A and B. And now, if the g function satisfy these two criterion, and then we got the existence conclusions, then the g has at least one fixed point in the interval A and B. So as you can see here, we have two requirements for the g. So first, we need it to be continuous. And then the second, we require that the range of the functions on this interval should be the subdomain or sub-range subsets of the A and B. And this is the two requirement here. If the g function satisfies these two requirements, and then we have at least one fixed point in the interval. And the next, this is just the existence. And then we are going to take a look at the uniqueness. The uniqueness here, so the setting things is the uniqueness. Unique. And we are going to impose one more criterion on the G function to get the uniqueness. So if in additions, so we are going to get one more requirement for the function G, and then we are going to get one requirement on the derivative. This is the derivative of the G, and then if the derivative exists on the AB interval, and there is a positive constant K, and then which is smaller than 1, and with this G prime, the derivative is bounded by this constant K. And this is the requirement here. It's about the derivative of the G function. And then for all the X on the interval A and B, we can just use the open interval here because the derivative should exist inside the interval. And if this criterion is satisfied, then we have the conclusions that then there is exactly one fixed point in the interval A and B. And this is the third criterion for this function here. And I'm going to skip the proof for this one today because we just need to understand the theorem well. So first part is the existence, and then the second part is the uniqueness. And then for the existence, we have two criterion: continuous and the range of the G. And for the uniqueness, we add one more criterion to the G function. That is, the derivative should exist, and then there's a bound for that derivative, and then the bound should be smaller than 1. This upper bound here. Does that make sense? So, any question about the statement criterion? Statements are here, and then about the criterion for the G function. There are several conditions on the G function, and this is quite important. It means that the derivative exists because sometimes the derivative does not exist. So let me just give you one example here. This is a typical case. So for example, you have, this is 1 and 2. And then this is a continuous function, right? But this one does not have any derivative here because it's a sharp point, right? This is the case. The G prime X does not exist on the interval AB. It means that, okay, the derivative exists here, but it doesn't exist at this point. And then it means that this criterion does not satisfy, cannot be satisfied here. Does it make sense? Okay, so I'm going to give you one example, and then you need to double check all the criterion here to check if these examples have unique fixed points here. So there's one function here, the gx function, and then the gx function is x squared and then -1 divided by 3. And then you need to show that this function has a unique fixed point on the intervals -1 and 1. So you need to check all these criteria here because it's checking the uniqueness. So first of all, I'm going to just show you let me see. Maybe first we need to show the first one, and then Gx is continuous. You can just state that because this is a polynomial, and then so it is continuous. And you don't need to use the basic calculus things to prove this one is continuous. You can just state it. This is a continuous function because it's a polynomial. And then the second one, and the second thing is checking the range of the functions g. So for the range of the function g, and then first of all, this is a parabola, and the maximums of the gx. And the minimums of the gx could be the endpoint, could be at the endpoints, and the critical points. So we need to find out the maximums and the minimum. And then next time we are going to use the maximum and the minimum to find out the range of the gx. And for the range of the gx, and then we require that it's inside the interval, it's a subinterval of the -1 and 1. And this is the things. So next time we are going to find out the maximum, minimum, and then we need to know the range of the gx on the interval a and b, and then we require this range to be smaller than to be a subinterval of the -1 and 1. And this is the thing. So this is the second step, and we are going to do this next time. And also for the third step, we need to calculate the g prime x, the derivative here. So, and then we require that there is a constant k, and then that is the upper bound k, and then it should be the upper bound should be smaller than 1. And this is the things we want to do the next time. We want to do the specific, the detailed calculation here for the gx function. And that's all the things we need to mention today. And we will keep finishing these examples next time. Thank you. Bye bye. If you have any questions, you can come over to ask me.
所以是在讲 power method， 不再是我们在会考吗？那次是上道题，也就是跳过。然后程序这个 index 有点就是不一样，跟我们就之前讲的都不一样。我看一下，程序是这个地方这个 tk 就直接是，就是这个东西是 k 加1，然后这个 index 是跟之前那个，但是我们前面学的都不是这样，因为这个地方 v0是等于20的，我们之前所有都是 v1等于20的，然后这个 x 就是这个。
你说这个退了一个，对吗？
对，然后这样后面那些 proof 呢也不是，就是如果说这个地方改了，然后跟着这个 index 的话，这个的 proof 也会有问题。